Yeah, so yeah, we talk about the some hardcore physics. Uh, yeah, at this one. So you can just feel like it's just a story. Don't really too serious if you feel like this is too difficult to you. Yeah. So here we talk about the magnetism of the Earth. As you know, we can use the compass to check the direction. Before we have a GPS, we will use the compass to check which direction is north or south, something like that. Yeah, so Earth is a huge magnet for point near Earth's surface. So its magnetic field can be approximated as the field of a huge bar magnet. So the magnetic dipole that stranded the center of the planet. But actually, we should be care something about, like, for the Earth we have geographic North Pole and geographic South Pole. Yeah, so this point R is called the geographic North Pole or South Pole. And in that case, the Earth is rotating according to this axis. And this is called the North Pole, and this is the South Pole. However, for the magnetic, geomagnetic North Pole or South Pole, so this is the geomagnetic North Pole and the South Pole. So for the Earth, the South Pole of the dipole is actually the north. This is actually the north. So this should be the magnetic South Pole, and this is the magnetic North Pole. And there are 11.5 degree difference between these two axes. Yeah, and actually this is actually the magnetic North Pole. So the magnetic field is coming from this point, and then like this going to the South Pole. Yeah, so figure shows the idealized symmetric depletion of the dipole field without the distortion caused by the passing charge particle from the sun. Yeah. So the direction of the magnetic field at any location on the Earth is commonly specified in terms of two angles. The field declination is the angle therefore found between the geographic north, which is toward 90 degree latitude, and the horizontal component of the field. So the field inclination is the angle up or down between the horizontal plane and the field direction. Yeah, and in that case, this magnetic field generated by the Earth is actually a shield of the Earth. It's actually the shield of the Earth, shielding the high energy particle like the gamma ray, or something like the X-ray, something like that. So as long as there are some high energy charged particle, it can try to shielding it. So you can imagine, as much as there are some charged particle coming from this side to the Earth, we can simply assume it to be positive Q. It doesn't really matter whether it's positive or negative, but as much as you can imagine, as long as it comes to this point, and then the magnetic field pointing in this direction, So you have learned the Lorentz force in chapter 28. So you know V cross B is pointing out of the page. So this is the Lorentz force pointing out of the page, which means that and as much as it go to the Earth, it will like shielding by the magnetic field. If your latitude is not too high, near the as much as near the 0 degree, or if you are close to it. So, but if you are at the place where your latitude is high, something like near the North Pole or near the South Pole. So suppose you have a charged particle at this point going to the Earth. And you can imagine the magnetic field in a similar direction to the velocity. And in that case, suppose you have V cross B. V cross B is something like V times B sine theta. Theta is the angle between the V and B. So suppose V and B has a small angle between them, and in that case, the Lorentz force will be small. And in that case, the charged particle will be injected to the Earth. So near the North Pole or near the South Pole, something like in the Northern European, you can see the aurora. Aurora in Chinese is called 极光. So actually, for the aurora, it is something like the high energy charged particle injecting to the Earth. So it try to ionize some of the atmosphere. And in that case, actually this is not good. This is not good. The high energy particle, if you accept too much, it will increase the probability to have cancer. So actually, the magnetic field generated by the Earth are actually protecting the people on the Earth. So, but the weak spot for the magnetic field shielding is near the magnetic North Pole and South Pole. So so sometimes when you see the aurora, it's very nice, but if you see too much, then actually you are increasing the probability that you are shooting by this kind of high energy particles, which is not good for health. So here we talk about something really hardcore in Thesis. So they try to find out what really generate the magnetic field. So here it talks about the spin magnetic dipole moment. Actually, in chapter 29, we have discussed that if we have some moving charge, or actually we have some current. Actually, some current is the moving charge. In that case, it will generate magnetic field. So, moving charge can generate magnetic field. So how come it will like that? So we try to see. So suppose we have one electron here, and of course if we move, it will generate magnetic field. But now we'll consider that an electron has intrinsic angular momentum called the spin angular momentum. Actually, in high school, the chemistry class, I suppose you should have learned some fundamental quantum mechanics. So for the quantum number, one of it is called the spin, the spin is like plus or minus 1/2 at the time. So you don't know how come it'll be like that. You just feel like, oh, it's just positive 1/2 or negative 1/2. So it is like rotating clockwise or counterclockwise, something like that. Actually, those quantum numbers are coming from solving the Schrödinger's equation. And yeah, for the original Schrödinger's equation, if you really solve that, you can solve the quantum number, angular quantum number, or something like that. I don't really quite remember. You can really solve 3 of them, N, L, and NL. You cannot still get the spin. You really need to add the relativistic effect so that you can really solve the spin from the Schrödinger's equation. So it is very difficult. Even the original Schrödinger's equation are difficult to solve. You need something called the Legendre series to really solve the Schrödinger's equation with the potential of a hydrogen atom. Yeah, so we just skip through all the theory and mathematics, so it turns out to be like that. So it tells you that as long as an electron is spinning, then yeah, of course there will be a spin angular momentum, or just spin, call it a capital S. So this is the S. So associated with this spin and intrinsic spin, magnetic dipole moment. So this means that as long as the electron is spinning, then it already generates the magnetic dipole moment. So by intrinsic, it means that S and mu S are basically characteristic of an electron. So intrinsic in Chinese, this is called 内在. So it is something like a philosophical problem. So as long as the electron exists, then the spin and also the spin magnetic dipole already follows the electron, like mass and electric charge. So mass is mass. So as long as I have a bottle, then there will be mass. As long as we have something else, there will be mass. So the spin and also the magnetic dipole moment already follows the electron. So the vector S and mu S are related by this equation. Of course, how it will be like that, you should really know how to solve the Schrödinger's equation with the relativistic effect. So this is way too difficult to explain it here. So the equation is something like that. So we have the spin. Spin, of course, is a vector, and then the mu S with a negative sign. So the mu S point to this side. This is E, the elementary charge, 1.6 times 10 to minus 19. M is the mass of the electron, 9.11 times 10 to minus 31 kilogram. So this is nothing but a fixed constant. And this is a spin. So this is the dipole moment for a single electron due to the spin itself. Okay, so for measurement along z-axis, the component Sz can have only the value given by ms. Ms is either plus or minus 1/2, which is the spin you learn in the quantum mechanics in high school. And then h is called the Planck constant, and h over 2 pi. Some of the textbook will use h bar to represent it. H bar. So this is called the reduced Planck constant. Reduced Planck constant. Because for many of the equation in the quantum mechanics, if you use h bar rather than h over 2 pi, then the equation will look easier. For this case, it is nothing but ms h bar. So it's just like F equals ma, something like that. So we only have a sz equals ms h bar. Yeah, here ms is nothing but 1/2 plus or minus 1/2. So it is nothing but 1/2 h bar plus or minus 1/2 h bar, something like this. Yeah. So this is s z in one of the direction, one of the axis. This s is in arbitrary axis. So this is difficult to imagine. This is difficult to imagine. So for an electron, the spin is opposite to the magnetic dipole moment. Yeah, so you can see s pointing upward, and then mu s pointing downward. So in the previous page we have mu s equals this one, and then sc equals this one. So we can just plug in this term into here, this term into here, and then also we plug in ms equals plus or minus 1/2. So we will have plus or minus 2 times 2 is 4 pi m at the bottom, and then e times h at the top. So this is the mu s, the magnetic dipole moment in z-axis, which is this one. So e, h, pi, m, 4 all are constant. So this is nothing but a constant. And this constant, we call it the Bohr magneton, which is like the unit of the magnetic field, or the magnetic dipole moment. So when an electron is placed in an external magnetic field, B external, and energy U can be associated with the orientation of the electron spin, magnetic dipole moment. Mu s, just as an energy, can be associated with the orientation of the magnetic dipole moment, mu of a current placed in B. So the orientation energy. So we have learned this before. It is like if we have a dipole moment, if we place at the external, if we have external B field, B external, and then we place this mu s inside the magnetic field, then there will be some energy stored in this system, and it will be like so you have this is the potential energy stored in this system, and still you also have the angular or the torque. The torque is actually mu cross B, if you still remember, in chapter 28 or 9, I don't remember. So that's the case. So when z-axis is taken to be the direction of B external, so we have this minus mu s z times B external is the energy stored in this system. So previously we just talked about the spin, and here, as much as you know, for an atom there must be a nucleus and also the electron. So as long as the electrons are rotating around the nucleus, then it is some sort of moving charge. So in this case, it will also generate the magnetic dipole moment. It is like you have the current going in this direction. So when it is an atom, an electron has an additional angular momentum called the orbital angular momentum, called L orb. So it's the orbital magnetic dipole moment. So orbital in Chinese is 轨道. Yeah, so it is actually related by this one, so quite similar as before. The only difference is that we have E over m times S. Here we have E over 2m times L orb. And yeah, when you learn the quantum physics, quantum mechanics, you also know that this is the quantum number. This is the quantum number. And this is the reduced Planck constant. So it is like ml times h bar. So this is the torque, or angular momentum. Actually, the orbital angular momentum of the electron. Yeah. So this is the magnetic dipole moment generated by this rotating electron over this axis. So we get some similar equation. Yeah, as much as if you put this inside the magnetic field, it will just have some oscillation and to store some energy inside the system. But yeah, still, if you really need to know why the equation should be like this, you should check the advanced quantum mechanics textbook. So it will be really difficult. Yeah. So next we talk about the three types of magnetism. So the first type is called the Diamagnetism. So in Chinese this is called 逆磁性. Diamagnetism. So a diamagnetic material placed in an external magnetic field, B external, develop a magnetic dipole moment directed opposite B external. If the field is uniform, the diamagnetic material is repelled from a region of the greater magnetic field towards a region of lesser field. So here you can see it is a levitating flock. So this is a flock, and inside the flock there are some diamagnetic material inside this flock. So here within this pipe we are generating some uniform magnetic field. And then actually these flock are floating in the air. So the flock is diamagnetic as is any other animal. So when the flock was placed in the diverging magnetic field near the top end of the vertical current carrying solenoid, so every atom in the flock was repelling upward away from the region's stronger magnetic field at that end of the solenoid. So the flock moved upward into weaker and weaker magnetic field until the upward magnetic force balance the gravitational force on it, and there it hung in the mid-air. So actually this photo is actually seen from top to bottom. Actually it is like we have a solenoid like this, and then the frog is placed here. I don't know how to draw, but actually it's floating. Actually it's floating because the solenoid will generate the B field, just say pointing upward. And actually for the frog, there are some diamagnetic material inside the frog, so it will generate. So this is called the B external pointing upward, and the frog will generate some magnetic field pointing downward. So it will feel like the frog will be floating. Okay, so actually the frog is actually floating in the mid-air. Yeah, the frog is hung in the air. So the frog is not discomfort because every atom is subject to the same force, and thus there is no force variation within the frog. So it is just like floating comfortably. So this is a funny phenomenon called the diamagnetism. The point here is that so if the diamagnetic material placed in the external magnetic field, it will generate some dipole moment direct opposite to the B external. So that's why it's called diamagnetism, 逆磁性. And the next one, the paramagnetism, in Chinese is called 双磁性. So a paramagnetic material placed in an external magnetic field developed by a magnetic dipole moment. So if the field is non-uniform, the paramagnetic dipole is attracted towards the region of the greater magnetic field from a region of lesser field. So for that one, it will generate the magnetic field, or it will just follow the magnetic field. So it is somehow like it is actually attracting by the external magnetic field. It is something like it is repelling by the external magnetic field. So the paramagnetic material have the atom with a permanent magnetic dipole moment, but the moment are randomly oriented with no net moment, unless the material in an external magnetic field be external, where the dipole tends to align with that field. So it is something like the dielectric. For the dielectric, there are many electric dipole inside it, but if there are no external E field, then it feels like it is a normal one. There are no electric field generated by that. But as long as there are some external E field, which means that if you just place the dielectric inside the electric field, then inside the dielectric, all the dipole moment will be aligned, and then will generate some E field, counteracting some of the external E field. Or you can regard it as the dielectric will store some of the energy from the external E field. For this case, it is similar. As much as there are some external B field, then the paramagnetic material will have the dipole moment aligned to the field. And so the extent of the alignment within a volume is measured as the magnetization. Actually I don't really know what it is, so there's only a simple equation called the Curry's law. So Curry's law. So she is the one to invent the X-ray. I suppose you may have learned it before. So in Chinese, she is called Judy Furen. So in the past, so she is called Mrs. Curry. Now, so she is renamed as. So we will call her the original name, the Mary Curry. So they don't really like this title. So it's not, So at that time, she find this called the Curry's law, which is the magnetization equals to the Curry constant times the D external over the temperature, the absolute temperature, which is this red line. So in a non-uniform external magnetic field, the paramagnetic is attracted in the region of the greater magnetic field. And actually, later, so when we really observe this phenomenon again with a much higher B external over the temperature, then we will find that this line will not follow this Curry's law anymore. It only follows the Curry's law up to this part. When B external over T is, for example, much larger than 1, it will start to saturate at this point. So this is called M over Mx. So there will be a maximum value for the magnetization. And actually for this phenomenon, we really need the quantum theory to really explain this. So so it's just for your information, even for me, I don't really know what is actually the theory explaining this. So for the classical physics, the physician try to write some equation as the linear equation, but it turns out that it will only be correct for some extent. For example, for the Newton's mechanics, it is correct when the velocity is not very high. When the velocity is too high, then we really need the relativity to explain the phenomenon. Just like when you use GPS, actually the GPS cannot only use the classical mechanics, cannot only use the Newton's mechanics. You still need the relativistic effect to make the positioning to be much more accurate. So here we have a simple sample problem. So for a paramagnetic gas at the room temperature, is placed in an external uniform magnetic field of magnitude B equals 1.5 Tesla. So the atom of the gas have magnetic dipole moment mu equals 1.0 mu B. Calculate the mean translational kinetic energy K of an atom of the gas, and the energy difference delta UB between parallel alignment and the anti-parallel alignment of the atom's magnetic dipole moment with the external field. Yeah, so when you learn the thermodynamics, you know K equals 3 second KT. 3 second KT. So it is 3/2 times the Boltzmann constant is 1.38 times 10 to minus 23rd power, and then the temperature is 300 Kelvin. So this is 6.2 times 10 to minus 29 joule. So this is the average kinetic energy for the gas at this temperature. So when we talk about the thermodynamics, it is something like the statistical dynamic. So usually we will talk about the average kinetic energy, root mean square speed, something like that. Yeah, so for the delta UB, it is like minus mu B 108. Cosine of 180 degree minus negative mu B cosine 0 degree. So we would like to find the difference between the energy difference between the parallel alignment and the anti-parallel. So this is the parallel, this is anti-parallel. Okay, so cosine 180 degree is -1. This is 1. So we have 2 negative, which is positive. And here we also have 2 negative, so we have 2 mu B. So this is the 2 times 9.27 times 10 to minus 24 times 1.5, which is 2.8 times 10 to minus 23rd joule. Yeah. Yeah, so this is the energy difference. Yeah, so next is the final one. This is called the Thesis, the ferromagnetism. So there are totally 3 types of the magnetism. So the ferromagnetism is the ferromagnetic material placed in an external magnetic field B external develop a strong magnetic dipole moment in the direction of the B external. If the field is non-uniform, the ferromagnetic material is tracked toward the So it is somehow like the paramagnetic material, but it has a more interesting characteristic. So so it is like, suppose we have an iron coil, and maybe we can just skip this one. So for the ferromagnetic material, it has an interesting characteristic called the hysteresis effect. Which is called 磁激效应. So so in the past we maybe still we're using some sort of hard disk, using the magnetic hard disk. So in that case, we try to store some data in the ferromagnetic material. So originally, when we don't apply the magnetic field to the ferromagnetic material, then it will not generate any magnetic field. But if we try to increase the external magnetic field, and even after that, the ferromagnetic material will still have the magnetic field. So it is like if we try to increase the magnetic field, B0 is the external. B0 is the external one. External magnetic field. So now we try to increase the magnetic field up to this point. And then we try to reduce the magnetic field. But the BM is actually the magnetic field generated by the ferromagnetic material. So it will still have some magnetic field remaining. Even we already remove all the external magnetic field. So it's like you can store a 1 or 0 in the area of the ferromagnetic material. So for this case, if we want to store a 1 here, we put some external magnetic field in one direction, and then after that, it will just store a 1 here. We can try to sense the direction of the magnetic field at that area. Then we can read this one out. And yeah, if we try to reduce the magnetic field or increase the magnetic field in another direction, so up to this point, and then and at this moment, the ferromagnetic material will not generate any magnetic field. And up to this point, the ferromagnetic material will generate the magnetic field in another direction for the maximum value. And now we can try to reduce the magnitude of the external magnetic field up to this point. So at this point, we perfectly remove all the external magnetic field, but still this ferromagnetic material will still generate the B field in another direction. So maybe assume we can just store a 0 for this situation. So we can try to read the magnetic field of that area then to see whether it's point to one direction or the other one. So it will stand for 1 or 0. And in that case, if you just follow this one, so it is not like a single line. In the past, usually when we learn some law, it's like a single line, but here it is not a single line. So it is called the hysteresis because it will follow this line and then go in this way, and then go in this way. Like this, so this is called the hysteresis. And for the magnetic hard disk, we use this theory for the data storage. And I think this is the end of this chapter.